To any of the other students?
Well, I mean, it would have been nice, but, you know, when I email all the students, I go through D2L.
Okay, yeah.
Makes it a little bit difficult. One click, one email, and I didn't have time to email however many there is, 28 of them or whatever. Those 3 emailed me, I sent it to them, so, yeah. Okay, so here's where we're at. Yes, I have your test graded. You'll get them back at the end. I got a little something to say about the test, and then before Saturday, I have to give you like a midterm grade that the university wants to see. I'm going to tell you how I'm going to figure that, all right? Where we're at is we're in Chapter 5. We were probably over a little halfway through there last Thursday when we finished. Remember the last thing we talked about was that little R squared that tells you the percentage of the variation in your response variable that's explained by the linear relationship, and I kept telling you how that was measuring how successful we were at fitting the line to the data. So what's left here in this Chapter 5, this idea of this regression and your least squares regression line, there's something called residuals. I'm going to put a special name to something we've already talked about. We never talked about outliers yet, and then there's some cautions at the end of this chapter. So the first thing I want to talk about is something called residuals. Okay. Now, if you remember, you probably don't remember, last Thursday when I was trying to fit the line to the data, we talked about these little errors, you know, those vertical distances from a point in your data set to the line. That has a name. It's called a residual, right? This is the vertical distance. That's the way I think about it. I probably used the term error last Thursday. Now, the reason we're interested in this and the reason we're going to call these residuals is because, look, that little r squared from last Thursday tells you how much of the variation we see in our y variable, our response variable, that is explained by the linear relationship, right? That's what it tells you. Okay, well, these residuals, these vertical distances, these little errors that we have, the distance from the line to a particular point, that's the leftover variation. That's what's left over after you fit the line and r squared percentage of it's been explained by the linear relationship. This is telling you about the scatter of the points about your line there. All right? So here's the deal. For every individual in your data set, every point that's on your scatter plot, there is a residual. And the way you calculate the residual is it is always the observed y minus the predicted y. Now look, if you back up a page in your notes, you've got that same formula, the observed y minus the predicted, and I called it an error. Right? Remember, this is from the data, and this is from your least squares regression line. That's what the line does. It predicts y's. Without all the words, it's always y minus, right? Remember, a y comes from the data. That's the observed y. Y hat is predicted by the line. That's coming from the line. That's nothing more than that vertical distance that the point is from the line. It's that error. It's called a residual. Now, what I would like to do is I want to look at example 5.5. All right, they're going to give us a different set of individuals here, 2 new quantitative variables, and then I want to calculate one residual for you. I want to calculate one vertical distance for you. All right, it says empathy means being able to understand what others feel. To see how the brain expresses empathy, researchers recruited 16 couples in their mid-20s who were married or who had been dating for at least 2 years. They zapped the man's hand with an electrode while the woman watched. That's the reason I had to do this example. I'm sorry. They zapped the man's hand with an electrode while the lady watched and measured the activity in several parts of the woman's brain that would respond to her own pain. Brain activity was recorded as a fraction of the activity observed when the woman herself was zapped. In other words, they're giving you like some proportion, right? Some fraction here. How much pain she actually felt in her head when she saw you get it compared to when she actually had it done to her. Okay? The woman also completed a psychological test that measures empathy. Will women who score higher in empathy respond more strongly when their partner has a painful experience? Here are the data for one brain region. Look, there's 16 subjects, right? This is all measured on the females, yes? You give them an empathy score, and then they gave them the brain activity. Remember, that was the fraction of the pain that they felt in their head when they watched you get it. So the first lady has an empathy score of 38, and she has a brain activity of negative 0.12. So the thing is, gentlemen, that's not the one you want to take home to mom. She didn't feel any pain when your ass got zapped. She enjoyed it. Now, the rest of them, their little fraction is at least positive. So they felt some amount of pain when they watched you. Dude, I'm thinking I want to marry number 16 or number 10 or something like that. You understand why I'm saying number 10 or number 16? Number 10 felt 0.745 of the amount of pain they felt when they watched you. The closer this number gets to 1, you understand the better, right? Yeah, so those would be the two I'd want to take home to mom. Now, my wife, if we did this, she would score 1. Remember, we're being videotaped, right? She might actually see this shit at some point. Sorry. Okay? Now, here's what we do. They've got the data for us. It's there. You know, there's the file. They give me the least squares regression line, right? Let's see if we can find this. What chapter is this? This is chapter 5, right? Just so that we can practice a little bit more with this. This is chapter 5. The title of it is Empathy 5.5. I'm assuming this is the same 16, it's that table, it's in the book there, right? So now what I would like to do is I'd like to make the scatter plot. What do we do with data like this? We make a scatter plot. We look to see if it's linear, right? We'd like to have the regression line if it looks linear. We'd like to have the correlation, yeah? So I'm going to go to graph, stat, regression. Remember, I want it all. I want the line on there. I want the regression line, everything. Fitted line plot. Now, you notice here they've got the empathy score as the explanatory variable and their brain activity as the response, right? Somehow they're thinking that maybe their score on that little psychological test will help explain what they actually feel in their brain, right? So the response variable here is the brain activity, and the empathy score is your predictor, your explanatory variable, your X. Okay? So you can see that we've got our least squares regression line. That's the same one here that's in the book, right? This brain activity is equal to minus 0.0578 plus 0.00761 times your empathy score times your X, right? I'm guessing you can see that the slope of that line is positive the way it's laid out. And look at the slope. The slope is the positive 0.007613. We would expect to see a correlation that's positive, right? Remember, if the slope's positive, the correlation's positive, they go the same. So we're seeing a positive association here, correct? Everybody agree? What does that mean? As the lady's empathy score increases, the brain activity increased, right? So the ladies that score higher on the empathy score actually felt more pain for their significant other. Yes? Remember, that was the question all this started with. So the answer to this question is yes, I am seeing that positive association. Now, before we get too carried away here, everybody see the R squared is 26.5? How well did we do at fitting the line to the data? No, remember, the closer that number gets to 100%, the better it is, right? So at 26.5, can we make predictions? Yeah, do we trust them a lot? Not so much here, right? Because that's trying to tell you there's a whole bunch of variation of spread about the points about the line, right? Because only 26.5 of the variation you're seeing in brain activity is explained because you have a linear relationship. We're seeing a lot of spread of the points about the line here. Okay? Now, let's pick one individual in the data set. Let's pick individual number 4. Right? I got everything for you there. I want to look at subject 4. And when I look at subject 4, what I see is subject 4 had an empathy score of, what is that, 55, and a brain activity of 0.369. Now, at this point, I'm hoping you understand that's the X and that's the Y, right? For that one particular individual in the data set, the empathy score was 55, the brain activity was 0.369. What I would like to do is for subject 4, I would like to calculate the residual. I'd like to calculate the vertical distance that point is from the line, right? So, if somebody asks you for the residual for a particular subject, the first thing to do is you got to know what the line is predicting for that empathy score. I'm going to assume it's not predicting 0.369. It's predicting something different, right? So we take our line, and my line looks like this, right? It's in the book. It was on the top of my little graph there. Minus 0.0578 plus 0.00761x. And so to make a prediction here for when the empathy score is 55, you plug 55 in. Right, and then that's going to give me a prediction, right? That's what my least squares regression line predicts for that particular empathy score, and you're going to tell me y hat is. He's working on it. Maybe. Tyler? So we're going to take 0.00. What is it? 0.4766 would be good, right? Now, remember, that's what was predicted by the line, right? Was 0.476. What we observed was the 0.369. So the residual is always the observed, a y, minus the predicted, a y hat. So you're going to take your 0.369 minus your 0.476. Did we get a minus 0.107? Right? So, it's telling you that you got a residual of a minus 0.107. The order is important. It's always the observed minus the predicted. It's always a y minus a y hat there. Okay? Now, the minus sign tells us something about where that point is on your scatter plot. If you stop and think about it for a second. What was the lady? The lady had 55 and had a 0.369. I would love for this to let me write on that, but it ain't going to. There's a little dot there, and that one at 55, there's almost two at 55, right? You see the one that's up higher, that's under the line? That's that subject number 4. The minus, anytime you get a residual and it's negative, that means you're below the regression line. Why? Because the predicted is greater than the observed. Anytime you get a positive residual, that means the point is above the line. What happens if you get a 0 residual? The line passed through that point, right? The observed and the predicted are the same. Okay? Now, was there anything special here about subject 4? Could I have done this for any one of these 16? And the answer is, yeah. Right? I just picked one. If I would have picked another one, what would have had to happen? The steps were the same, right? Whatever subject I picked, they have an empathy score and they have a brain activity. Right? You have an X and a Y. You got to plug the empathy score in to see what the line is predicting and do the subtraction. There was nothing special about subject 4. We could have done any of them. All right? Now, on page 140 in your book. They give you all 16 residuals, right? Right here at the top. First paragraph down there, residuals, there's all 16 of them. Okay? Now, just so you have it in your notes, there is a residual for each observation. If there's 16 subjects, there's 16 residuals. If there's 72 subjects, there's 72 residuals. Now, the other thought is, just out of the blue here, the mean of the residuals anytime you do this, if you take the mean and the residuals, in other words, add them all up and divide by the total number, you'll get 0. If you stop and think about what I told you before about the least squares regression line being the best fitting line, the one that makes all those vertical distances as small as possible, you shouldn't be shocked if there's the same amount of residuals above as there is below. Right? It's the best fitting line. The way to say it is, the mean of the residuals is 0. Take that average, you get 0. Okay? Now, there's a little graph that goes along with these residuals. All right? And there's something called a residual plot. It looks like this. You always put your explanatory variable on the x, we know that. But instead of putting the response up the y, you put your residuals. And then you come here and you put this little 0 residual in. Now, that right there corresponds to the least squares line. Look, this is another scatter plot. It's the residuals versus the explanatory variable. The 0 residual is actually where the regression line sits now. Okay? Now, obviously, if we had to, we could do it by hand, right? Find all 16 residuals, put the explanatory variable on there, put the residuals on there. But I'm going to come back here for a second, okay? And I'm going to X this out, but I'm going right back to where I was, okay? That's where I started all that, right? And I want to go to graphs. You see at the bottom right-hand corner it says residuals versus what variable? If you'll click in there, put your explanatory variable in there, right? It's always your explanatory variable. That's the residual plot that we work with in this class. It's always the residuals versus your explanatory variable. All right? So I went to graphs. I just put residuals versus what variable? Empathy score. Okay, there's the original one. There's your little residual plot that's on figure 5.6 on page 140. You're plotting the residuals, right? You're seeing how far the points are from the line. You're giving me a visual of those 16 residuals on page 140. Okay? Now, bear with me for 3 minutes here. What good does the residual plot do for us in this class? Well, what we would like to see, because remember, why we want the regression line? We want to make predictions, right? We want a value of x. We want to predict the value of y. What we would like to see, I would like to see a residual plot that looked like this. I'm not going to label things on you. You're going to know the explanatory goes on the x, the residuals go on the y. What I would like to see is Does anybody know why I would want to see that? Does anybody understand why I want the residuals all to be small? That means the line fit the data really well, right? Remember what we're looking at here. You're looking at that spread of the points about the line. Yeah, right? So what I would like to see is there's this nice spread of the points. Not very far away, just a nice spread. Then how do I feel about making predictions? I feel good. But the problem is this. You'll already know you're going to see a residual plot like this by r squared. Because I can tell you right now, r squared is... Right? I can tell you by looking at that residual plot that if I had actually stopped to look at r squared is going to be high, like 90%, 85%. We would have known already that our predictions were going to be good. R squared, a high r squared will produce a residual plot like that. Why? Because a high r squared is telling you almost all the variation you're seeing in responsive variables is explained by the linear relationship. There's not a lot of scatter of the points about your line there. Yeah? So the residual plot ain't adding nothing to anything when r squared's high. So then why would I want to look at it? Well, let's say r squared's not good. Right? Let's say it's low. 20%, 10%, 15%. Do we just throw everything away? No. This is where you would stop and you would look at the residual plot. And what you're looking for is something like this. So we don't throw everything away. Now, how do you feel about making predictions? How do you feel right here? The line fit the data really well for those values of x, right? How do you feel out here? Okay, I'll be honest with you. I feel good about making predictions here. I feel bad out here. Does everybody understand why I feel bad out there? The line didn't fit the data. R squared would have come back low. R squared doesn't know that there's a chunk of the values for the explanatory variable that the line fits really well. It doesn't know that, right? The residual plot knows that, oh, maybe there's a range of values that the line fit the data really. Look, I'm trying to come up with some reason for looking at a residual plot, and this is my reason here, is that, okay, my r squared's not good. You know, my r squared's down low. I don't feel good about making predictions for the entire range of x values. Maybe it's good on one end or the other. Maybe it's good in the middle, and then you could predict there. See, I always got this little thing running in the back of my head that we just gave some guy $5 million to do some research, and he gets something that looks like this. You know, whoever gave him that $5 million is not going to be happy if you got to throw everything out, that you couldn't get anything. Well, no, I got something for you. We're good in that part. We're just not good out there. Right? That's the kind of thing I have running in my head here. Can we salvage anything out of what happened? Okay? Again, what do I really want to see? That's what I want to see. Right? If I see that, r squared's low, we can still salvage something. Let me ask you this. One more picture. All right? Let's say you look at a residual plot. Okay? And the reason, like I say, you know what you're going to see when r squared is good, when it's high. You're going to see that nice tight pattern. When r squared's low, what happens if you see something that looks like this? Do you have any idea what you did? Now, I'm going to give you, obviously, again, what you did is you tried to fit a line to a pattern that was not linear. You tried to fit a line to a curve. You see the curve in there? That'd be the same kind of curve you'd be seeing in your scatter plot. Right? Tried to fit a line to a curve. That's a no-no. Would you have known this before this point? Remember how it goes. You do the scatter plot, you look, right? You calculate R, you look at R squared. Hell, R is bad here, right? You got some R that's like close to 0 if you tried to fit a line to something that looks like that and gave you that residual plot. Okay? Now, one of the things we've never talked about here, I have talked really, really little about what's called influential observations. They're outliers. All right? Now, I'm going to kind of do this my own little thought here. And when I think about influential outliers, okay? So the first thing is, outliers in general on a scatter plot, when you're looking at these two quantitative variables, they can be extreme. You got all kinds of choices here. They can be extreme in the X, the Y, or both directions. Now, that's just outliers in general. Hell, that's just like being stuck out in the tail in a histogram or a stem plot, right? They're extreme in that direction or that direction. Well, remember, you got an X direction and a Y direction. It might be just extreme in the X. It might be extreme just in the Y. Or, hell, it might be extreme in both of them. I don't know which end it's on. Okay? Now, instead of me getting all carried away here and looking at their examples, what I want to look at is on page 143, there's a box there. All right? And it says this, influential observations. First off, you've got to get stuck in your head that an influential observation, influential outliers, it's an outlier to start with. Right? That's the reason I put outliers there. They're influential, but they are also outliers. It's trying to tell you that you have outliers that are not influential. All right? It says an observation is influential if for a statistical calculation, if removing it would markedly change the result of the calculation. Now look, the only two calculations we're looking at here is correlation and the least squares regression line. So the only way to actually know if you have an influential observation is to do it with it, take it out, and see if your calculation changes. It says, the result of a statistical calculation may be of little practical use if it depends strongly on a few influential observations. In other words, if I can put a couple points in here and all of a sudden my little R squared gets good and everything looks linear, then you really don't have anything, right? If it's based off of like two observations that are influential. Now, the important part to me is the next little part. Points that are outliers in either the X or the Y direction are often influential for the correlation. In other words, what it's telling you is not always, usually points that are extreme in the X or the Y have an influence on the correlation. Points that are outliers in the X direction are often influential for the least squares regression line. Only the X direction, right? Something that's extreme in the X will move the line a bunch. Something that's extreme in the X or the Y will change the correlation a bunch. Okay? Now, here's the way I wanted to attack this. Yeah, I know there's an example 5.6 here about influential observations. No. I'm not interested in putting any data to this. I'm interested in showing you what's going on here. All right? So what I've done is, look, you know, I'm in Launchpad here in case you don't know. I'm going to back up to I'm on my first thing here. And I'm assuming you guys see a little resources tab over here. I just want to show you where I got this from. Resources. Damn. No, I want to do this. I want to show you exactly from the beginning. Remember, I'm the teacher. I got all kinds of students. Right, so if I go to resources at this point, hopefully it comes up like that. And I want content by type right here. And then I'm going to come down until I find what's called statistical applications. The only one I'm going to use all semester on is this one I'm getting ready to show you. And then I want the one for correlation and regression, right? Okay, so that was under resources, content by type, statistical applets, correlation and regression. And then if everything works right, it opens up this little window here, and it'll allow me to put little points on here, and we can see how the correlation changes and how the least squares regression line changes, right? So I always come here and I click Show the Least Squares line. In other words, put the line on there for me. So I'm going to start here. I'm going to put a point. Anybody shocked there's not a line yet? How many points does it take to make a line? Well, let me ask you this. When I put the next line on there, what's the correlation going to be? Yeah, I'm getting a little mathematical for some of you, and I apologize. Of course, every line, I can put a line through 2 points. It's got a positive slope. It's got a positive correlation, right? So what happens is I start adding points here to kind of fit the linear form. Obviously, things aren't perfect, right? You know how the book said that points that are extreme in the x direction are usually influential for the regression line? You see that picture right there? Something extreme in the x would be something that is out here, right? See my cursor? Did the line move a bunch? That's what the book's talking about. See that point, that last point I just put on there? That was influential for the regression line. What did it do? Here's the thing. When it's influential for the regression line, it pulls the line towards it. Yeah? Everybody see that? Can I make that one disappear? Moved it back. What's what happened to the correlation? The correlation is 0.9459. Do you think the correlation is going to get better or worse when I put this guy extreme in the x? He's going to get worse. 1 point's trying to tell you, hell, you ain't even looking at something that's linear now. Right? The correlation went down to 0.1448. That's what the book means by markedly would change the statistical calculation. Now, I'm cheating here. I'm not calculating. It's doing it for me. But that 1 point that it was extreme in the x moved the line a bunch. It was influential for the regression line. It changed the correlation a bunch. What about if I get something that's extreme in the y, like up here? You think it moves the line a bunch? You think it changes the correlation a bunch? And the answer is yes to one and no to the other. It hurt the correlation, but did the line move very much? Not like the other direction. That's the reason your book says usually a point that is extreme in the x direction is influential for the regression line. Extreme in the x or the y is influential for correlation. All right? So I go at it like that. Now, I'm going to clear this, and I'm going to do this to you. So I got these points here, right? Let me put my line back on there. Now, my correlation is 0.2983. That's not too good, is it? Let's come up here and put a couple points. You remember when I just told you that if everything depends on 1 point, then it's probably useless? Did you see it go from 0.29 to 0.88 by me putting that 1 point on there? That 1 point is trying to tell you things look more linear based off of that 1 point. Yeah? So is that point there influential for correlation? Yeah. What about the regression line? It didn't move much. Right? That's the flip side of it. Before I had a nice linear pattern and I was sticking somebody out here. Now, here I had hardly no linear pattern and I start adding points that are extreme and I'm starting to make things, my calculations are starting to look like things are linear when they're really not. That point there is influential for the correlation. Okay? That's the other side. Now, what you're going to see, and the way we usually ask these kind of questions, is we give you one that looks like this. And then we stick a point out there. And we ask you see that point to the right there? Is that influential for the regression line? Well, yeah, it is. You just saw me move it a bunch. Now, if you're calculating it, like you take that point out or you put that point in, you understand the slope and everything changes a bunch on your line, right? That's what happens. That's what's going on there. The slope was here and then the slope was down here. The slope changed a bunch. I guess a bunch is probably not the right term, the slope changed markedly. That's what the book would say. Okay? I just wanted to show you that. That stops me from drawing all the pictures. It's just, that's it. That's what's going on. That's what's happening. Now, I do want to write one thing over here for you. And the one thing I want to write over here for you is a point. Let's do it like this. It's not just a point. Hell, it's an observation that is influential for the regression line usually, I'm not even going to say usually, for the regression line has a small residual. In other words, you're not going to pick it up in the residual plot we were talking about. And why does it have a small residual? What's that influential observation do? It pulls the line towards it, right? So it's making that vertical distance small. It pulls the line towards it, producing a small vertical distance, a small residual. So you won't see it in the scatter plot. It's going to be in the residual plot. And if you're not really paying attention, you might not even see it in the original scatter plot you start with, right? It might be completing the pattern like those last ones I showed you there. Okay? So look, that's how I think, and that's what I think about with influential observations. It's just less drawing for you, that you can see what's going on when I start putting points on there and moving things. Now, there was nothing special about everything I drew having a positive one, right? I mean, I could have started drawing the points like this and gave you one that was extreme over here and it had done the same thing to you, right? So this is what I'm saying. If I would clear this one, and, if I would have had a... So, I got a negative relationship here, right? And all of a sudden, something extreme in the x would be over here. Look, it took the line from having a negative slope to now having a positive slope, right? Extreme in either direction, depending on what you're looking at here, okay? Now, the rest of this chapter. That was my two big thoughts here, was the residuals, and then that idea of this particular kind of outlier that actually changes your calculation a lot, right? The rest of this is cautions, things you need to be aware of. Because, look, at this point, I always tell the students, there's nothing ever stopping you from calculating correlation and the least squares regression line. At this point, the only thing that's stopping you is you got to have two quantitative variables, right? Software, you give me two quantitative variables, I can calculate the correlation, I can calculate the regression line. But there's things to be aware of, right? So I guess the book calls them cautions. What I want to call them of is beware. Do you trust what you're looking at? Right? So I'm going to start like this. Cautions. All right? And it's always cautions, and just so you know, it's cautions about correlation, and regression. I probably got about 5 of them here. All right? So the first one is, they describe only linear relationships. Now, how do we know that? The correlation tells you the strength and direction of your linear relationship, right? That's what I keep preaching at you. The regression line, what the hell is it trying to do? You're trying to fit this line to this linear form. It's only going to tell you about linear relationships, linear forms. That's all these two are good for. Anything else, we've got to have something else. All right? 2, they are not resistant. Now, it's been a while since I used that kind of term. When I tell you something is not resistant, it's telling you they're influenced by outliers. Does anybody remember the talk we just had 3 minutes ago about influential observations? That's what we're talking about, right? These are your influential observations. Right? The ones that would change the correlation a bunch, the ones that would change the regression line a bunch. So how do you know we're looking that we got influential observations? Okay. Always make a scatter plot. And what you're looking for is, you look for influential observations. You look for ones that are extreme in the X or the Y, or hell, maybe even both. And then you say, well, are they really? Well, then you calculate everything with them, you take them out, and see if things change a lot. And if they do, they're influential, and you know that you really need to pay attention at that point because they have a big influence on our correlation in our regression line. That was the reason I used that little applet for you back there, because I thought that would help that story. Okay? So that's the first 2. Number 3, I have said this before without using this term, and the term is extrapolation. In English, that means trying to predict outside the range of X values in the data. Now, I screamed at you about this last week, that you don't want to do this. You're looking at the scatter plot, right? And you have this range of X values. We don't go outside of that. That's extrapolating. That will get you in trouble. And the example to hopefully help this stick in your head is, let's say that I've measured 2 variables on kids from 6 to 16, right? I've measured their age and I measured their height. Yeah? And so down here, I know I go from 6 to 16. This is their age. And then I measured their height. Right? Now, you do understand as the kids get older, they get taller, right? So I should be seeing a positive relationship. I should be seeing something that looks like this. In general, yeah? What do you then when we fit the line to the data, we're going to see a regression line that looks like, what happens if I try to predict somebody's height when they're 25 years old with this? Let's say 25 is out here. I predict them to be like 10 feet tall or something. Yeah? Because especially when we have a variable like this measured over time, usually things are only linear for some amount of time. You know that it really doesn't do this. You do know what happens, right? About 16, 17, or 18, we level off, right? It doesn't keep going forever. So this is my example of why you don't want to do this. You don't want to extrapolate outside. You don't want to predict outside the range of X values in your data, because this will get you stuff that are like crazy. You know, with this one here, the guy's 25 years old. Hell, he's 10 foot tall. We know that's not true, right? Especially beware when you have your variable measured over time like this. One more time, usually things, if they're linear over time, they're only linear for some amount of time, not forever. Okay? Can I say here? Don't do this. We don't extrapolate. We don't go outside those range of x values. Now, that's 3. Number 4. Now, the term is lurking variables. It's on page 147. Okay? And it says, is a variable that is not among the explanatory response variables in the study, yet may influence the interpretation of relationships among those variables. These are variables not measured. We're not using them. That may influence the relationship. Now, it may influence them it can go either way here. It may strengthen the relationship if we ignore them. It may make the relationship weaker if we ignore them. All right? So look, I started you this on chapter 4. Do you remember we were talking about woman's height and her risk of heart attack? Yeah, and we didn't talk anything about her diet or exercise, all that stuff. Those were lurking variables. And so the one I want to look at is this. I'm on page 147, example 5.7. Right? I want to look at the one in the book. The Kalamazoo, Michigan Symphony once advertised a Mozart for Minors program with this statement. Question, which student scored 51 points higher in verbal skills and 39 points higher in math? Answers, students who had experience in music. Who knew it? Now, the reason I like some of these examples at this part of this chapter is if this author put them in there, they're real. It's not like he's making this up. They actually advertised that. Who would have thought that there's this positive relationship between math skills and verbal skills and music? When you see something crazy like this, maybe it's not crazy to you. When I see something crazy like this, I'm starting to think, okay, so what variables did they happen to forget to measure and look at here? It says, we could as well have answered student who played soccer. Now there's one. Play soccer, you get better verbal skills, higher test scores on verbal skills, and higher math scores. Didn't know that. Why? Children with prosperous and well-educated parents are more likely than poorer children to have experience with music and also play soccer. They are also likely, now the ones I'm getting ready to list, here comes your lurking variables. They are also likely to attend good schools, get good health care, and be encouraged to study harder. These advantages lead to high test scores. Those are lurking variables there. Okay? These advantages lead to high test scores. Family background is a lurking variable that explains why these test scores are related to experience with music and to soccer. Okay? What was the other one I was going to give you? That's the only example he's got there. It turns out that there's a really strong positive correlation between a kid's shoe size and their reading comprehension. You know why? What's the lurking variable there? Age. Yeah, the older they get, the bigger their feet get, the better they read, right? There's a lurking variable there, yeah? You see all kinds of stuff like this. Sometimes you just got to stop and... you understand why the Kalamazoo, Michigan Symphony wanted to advertise that, right? I do. They wanted kids. Now, was that number 4? Number 5. Not so much a caution like the other ones, but association, that means a relationship, does not imply The book's going to call it causation. So I'm going to underline the not. What they're talking about is, when you hear me say the word causation, I always try to follow it with, we're looking for cause and effect. Right? What we're looking at is, if we make changes in our explanatory variable, does that have an effect on our response variable? Does making changes in the explanatory variable cause a change in the response variable? When somebody's talking to you about causation, that's what they mean, cause and effect. If I start making changes in your explanatory variable, will that actually cause a change in your response? Will that have an effect on your response variable? Like the number of beers you drink and your blood alcohol level. That's causation, right? That's cause and effect. I start changing the number of beers you drink, I'm going to start changing your blood alcohol level. Yep. And so the example they have here is example 5.8. I always like this one. And I'm assuming the older I get, the more I'm going to like this one. A serious study once found that people with 2 cars live longer than people with only 1 car. Owning 3 cars is even better, and so on. What they're trying to tell you is that there is a substantial positive correlation between the number of cars X and the length of life. So they're telling you there's a strong positive association between the number of cars you own and how long you will live. So before I read any further, does that mean if I start buying more cars, am I going to live longer? No, there is no cause and effect here. There's no causation, even though there's a strong positive association. It says the basic meaning of causation is that by changing X, we can bring about a change of Y. Could we lengthen our lives by buying more cars? No, the study used number of cars as a quick indicator of affluence. Well-off people tend to have more cars. They also... Now, the next line I'm getting ready to read, you remember number 4, lurking variables? We're getting ready to talk about lurking variables. They also tend to live longer because they are better educated, take better care of themselves, and get better health care. The cars have nothing to do with it. Those 3 things I just listed, those were lurking variables. They picked out the number of cars. They should have looked at the other 3. Yeah? Actually, in an older version of this book, we didn't use cars. It turns out there's a strong positive association between the number of TVs you own and how long you live. I always like that one. That's a little cheaper, right? Go out and buy 30 TVs, live an extra 20 years. No. What's the deal? It's the same as the cars, right? Those people are better. The more TVs you own, the better you're educated and all that kind of stuff. All right? That's a no-no. Now, I'm not interested in the next 2, but here's the deal with this, all right? This is leading us to future chapters. The best way to get good evidence that changing X, I'm just going to give it to you in terms of X and Y, changing your explanatory variable causes changes in your response Y, right? That's what we're talking about with cause and effect, is to do an experiment. And if I remember right, experiments are chapter 9, I think. Yeah. We spend a whole chapter on the right way to do this, the right way to find evidence of cause and effect, the right way to see that if you start making changes in your explanatory variable, it actually causes a change in your response variable. So I'm hoping at this point you understand whatever we do in Chapter 9 about experiments, we got to do something about the lurking variables, right? Because that's the problem here with causation. Now, the last thing in this chapter, example 511. There are just certain things that nobody's going to let you experiment on. One of them is, you ever heard the thing about, that children that live under power lines get cancer? Yeah. Are we going to take 10,000 children and build them houses under their power lines and see if they get cancer? You ever heard the little story about smoking causes lung cancer? Well, for me to do an experiment on that just off the top of my head, I'd have to have like 100,000 people. 50,000 of them are never going to smoke. The other 50,000, I'm going to make smoke a pack of cigarettes a day for 30 years. You want to let me do that to anybody? And the answer is no. But sometimes, even without an experiment, the evidence is overwhelming. That's example 511. Does smoking cause lung cancer? Despite the difficulties, it's sometimes possible to build a strong case for causation. So strong that the federal government will put it on my can of Copenhagen. Right? In the absence of experiments. The evidence that smoking causes lung cancer is about as strong as non-experimental evidence can be. Okay? It says, doctors had long observed that most lung cancer patients were smokers. Comparisons of smokers and similar non-smokers showed a very strong association between smoking and death from lung cancer. Could the association be explained by a lurking variable? See, that's what would have to happen here. There'd have to be a lurking variable if we don't have causation between smoking and lung cancer. It says, might there be, for example, a genetic factor that predisposes people both to nicotine addiction and to lung cancer? The tobacco companies were hoping for that, right? Smoking and lung cancer would then be positively associated even if smoking had no direct effect on the lungs. Here are how the objections were overcome. Now, they got a list of things here. It says the association is strong. Have you ever seen anybody tell you that smoking doesn't cause lung cancer? No. 2, the association is consistent. Many studies of different kinds of people tell you the same thing. Higher doses are associated with stronger responses. People that smoke more cigarettes get cancer sooner, more likely to get it. Now, you're supposed to have in the back of their head, everybody knows this guy that's 97 years old. You know him? He smoked 7 packs of cigarettes since he was 3. Ain't even seen lung cancer. Right? And then we know the other people that have never smoked and have lung cancer. What are those people in this? Those are outliers. Right? Those are your outliers. Okay? It says the alleged cause precedes the effect of time, right? It happens over and over again, and the alleged cause is plausible. Now, they won't let me experiment on humans, but they'll let me experiment on dogs and cats and rats and things like that, right? That's the deal. Okay? Look, the reason I want to do that last part is because, we're not far off from Chapter 9, experiments. So, that's not the last time you're going to hear me say things like experiment, cause and effect, causation. All right? Now, there's one chapter to go here. And I want to get it started tonight, and we'll finish it on Tuesday. I kind of want to get us thinking about this. And it's chapter 6. Now, remember, I kept telling you that chapters 4 and 5, they go hand in hand. Right? They're all about 2 quantitative variables and the relationship between them. We were really interested in linear relationships. We calculate correlation, regression line, use it to predict, all that stuff. Chapter 6, the title of it is Two-Way Tables. Now, here's the difference. No more quantitative variables. When somebody tells you you're looking at something called a two-way table, you're looking at 2 categorical variables. That's the first thing. Like their gender, their race, their occupation, their hair color, their eye color, what age group do they fall in? Something that puts you in a category. We're looking at 2 of them. What we're interested in this chapter is the relationship between 2 categorical variables. That's what's going to happen here. All right? Now, when we're trying to analyze categorical data, I don't care if you're looking at one categorical variable or two of them, right? When you try to analyze categorical data, we use counts or percents. Now, you're going to see me every time I do something here, I always like the percents. And I'm going to be honest with you, the percents are more informative than some count, right? So you're going to see me always want to calculate percents. You're going to see me when I make bar graphs, the heights of the bars are always percents. I like the percents way better. They just work better here. Now, this example 6.1, I'm going to use it here to get us started tonight. Example 6.1 says the following. It says, a sample survey of adults age 18 and over. In other words, they took some random adults, right, that are over 18, and they asked them the question, if you were free to do either, would you prefer to have a job outside the home, or would you prefer to stay at home and take care of the house and the family? Table 6.1 shows the responses. Now, table 6.1 on the next page, that is a two-way table. Because what that table does, and the reason we like to call it a two-way table, is it classified everybody in this that answered this survey by both variables. It classified them by what is it? Their age, by their preferred lifestyle, and by their sex and education, right? There are two categorical variables there. Now, anytime I'm looking at a two-way table, I know I'm classifying by two categorical variables. There's going to be what I want to call the row variable. That's how the rows are chopped up. And there's going to be a column variable. That's how the columns are chopped up. So in this case, my row variable is, how's the rows broken up? By their sex and education. Now look, it was either males or females and college or no college. And the column variable, how are the columns broken up? I'm just going to say lifestyle. A job outside, or a job in, what does it say? The job outside the home, stay home and take care of for the house and family. And then the last one was no preference, right? You didn't pick either one of those. Those are both categorical variables. The row variable, how's the rows chopped up? By sex and education. The column variable, how's it broken up? By their lifestyle. What would be their preferred lifestyle? Now, while I'm sitting here and looking at that table, I got to give you some more of way I think about this. Does everybody see that there are 4 choices, 4 categories, 4 groups for the sex and education? Right? There's 4 rows in the table. Yeah? And there are what? 3 columns in the table. There are 3 choices for the preferred lifestyle. I understand there's a total on the row and there's a total in the column. That's not what I'm looking at. That's got nothing to do with what I'm looking at. What I'm looking at is there are 4 rows. There's 4 values for sex and education. There are 3 columns. There are 3 preferred lifestyles. So when I see that, there's 4 by 3 table. It's always rows by columns. The number of rows by the number of columns, and I don't care anything about the total. I'm actually looking at the variable there. They were nice to us and added things up for us. I don't care about that when I count my 4 by 3 table. That means there are 4 times 3, which is equal to 12 cells. Right? So a two-way table is always the number of rows by the number of columns. Multiply those 2 numbers together, and then there's so many cells in this table. Right? If it's 4 by 3, there's 12 cells. If it's 5 by 3, there's 15. If it's 5 by 2, there's 10. Right? I'm actually looking at the body of the table here. And this is how I would label them. If there's 12 of them, I would go 1, 2, 3. I start numbering at the first one and all the way till I get to the end, and then I come and start numbering again, right? So that's the cells. So the first cell is the ones that said job outside of home that were women and no college, right? And I can see that cell 6, well, where's cell 6? Cell 6 is, that was the women that had college that said no preference, right? It's just a nice way of keeping track of things here for us, okay? Now, the first thing we're going to do here is we're interested in, there's different types of distributions here that we can calculate based off of that two-way table. Now, does everybody understand that that's just counts, right? Those are just a number of individuals. And I guess if we read a little further here, that maybe that's the total number of people. I don't see where they rounded anything off or chopped anything off, right? So there was 81 people that were women with no college that said job outside home. Everybody read that fine? There are 32 that were men with no college that would stay at home and care for the house and family. Everybody see where I'm reading the table, right? Does everybody see that there was 195 women with no college? That's the row 1 total, yes? Does everybody see that there was 332 that said stay home and care for house and family? Yeah, that was the column 2 total, yes? So there's a bunch of numbers running around in this table, and they're all counts. It's just how many, okay? So the first type of distribution that we can deal with when working with a two-way table is something called a marginal distribution. Now, any two-way table that you're looking at, there are always 2 of these. I don't care if it's 4 by 3, 72 by 13. There's always 2 marginal distributions to be talked about. And what we do is we look at each variable separately. You ignore the other one. Now, I'm going to write something in parentheses here. Folks, you've already done this. You've already had a categorical variable, and you've already told me the percentage that fell in each one of the categories or groups. Hell, that was chapter 1, right? We've already done this in chapter 1. I understand that there's 2 there, but we're going to ignore one and just look at the other. Now, the screwed up part, you see marginal. The reason they're called marginal is because we use the numbers that are in the margin of the table. Yeah, I know that sounds way too easy, but that's what you do, right? You're either using row totals or you're using column totals. That would ignore, if you look at row totals, you're ignoring the columns, right? If you look at column totals, you're ignoring the rows. Yeah, so there's 2 of them to be had here. So let's look at one of them. The book gives you one of them, the marginal distribution of the sex and education, right? I want the marginal distribution of lifestyle. Example 6.2 gives you the marginal distribution of sex and education. That's the other variable, right? In other words, example 6.2 gives you the marginal distribution of your row variable. I want to give you the marginal distribution of preferred lifestyle, which is your column variable. Now, anytime somebody's talking to you about a marginal distribution, you have to know how many individuals are in the table. If they've actually added everything up for you, that number is in the lower right-hand corner. How many individuals are in this table? 1,012, right? So, when I think about marginal distribution of lifestyle, there are 3 choices for lifestyle. It's either outside the home, or at home, or, what was it, no preference? There's going to be three percentages that we're going to calculate here. Now, the reason I focused your eye on the 1,012, because what we're getting ready to look for is how many of these individuals in this table said they would prefer a job outside of the home. That is that first column, right? All those people in that first column said a job outside the home. I don't care if they were men, women, no college, or what. Everybody in that table said job outside the home. How many people are there? How many individuals fell in that particular column? There are 645. How many is in the table here? I want to know the percentage that is in this table that said job outside the home. There are 645 of them that said that. Out of how many? Out of everybody in the table, which is 1,012. What do I get there, bud? I get 63.7%. Now look, when you punch 645 divided by 1,012 in the calculator, you're going to get 0.637. Move the decimal place 2 to the right. Now, what about home? What about the ones that said stay at home and care for house and family? How many individuals in this table said that? That's the second column, right? And there's a total number of 332 there. So what's the percentage that said that? If there's 332, it's out of the total number of 1,012. 32.8. And then finally, the ones that said no preference, that's the third column. There's 35 that said that. Out of the still 1,012. And I give me a percentage. That's a small one, right? What was it? 3.5%. I ignored the row variable. I just focused in on the columns, and I am taking the column totals divided by the table total here. Everybody understand that, right? 645 was the column total that said job outside the home, right? The 332 was the ones that said stay at home and care for the house and family. The 35 was the ones that said no preference. That right there is the marginal distribution of preferred lifestyle. 63.7% of the people in this survey, in this table, said job outside the home. 32.8% said stay at home and care for the home and family. 3.5% said no preference. Yeah? Did I ignore the other variable? Look, folks, I could have gave you this problem back in chapter 1. I could have said, well, look, I got this variable of preferred lifestyle that we asked these people. I'd asked 1,012 people this question, and 645 said they would prefer a job outside the home. 332 said they would like to stay at home and care for the home and family. And 35 said no preference. It didn't matter to them. There's your distribution, right? There's your distribution of preferred lifestyle. Yeah? If I add those three percentages, what do they add to? You understand that if I take these three together and add, why? Because everybody in this table picked one of those three preferred lifestyles. Yeah? Now, don't freak out. We rounded stuff off here, right? You know, I rounded off. I'm assuming he rounded off to 63.7. There was more places out there. Don't freak out if you get 99.9. Don't freak out if you get 100.1. That's just where you rounded things off. As long as I'm close to 100, you've done things right. You had it set up where you got perfect, right?
Yes, we did.
Yeah, that's cool. I was glad you did that. Right? Now, could we have ignored the columns and done the rows? Now, you notice when I'm doing a marginal distribution, the table total is a denominator here. And then if you're looking at the column variable, the column totals are your numerators. Everybody see example 6.2? How many percentages are you going to get there? You're going to get 4. Why? There are 4 rows, right? There was women no college, women no college, men college, right? You were getting 4 there. So there'll be 4 percentages because the variable sex and education has 4 categories or 4 groups. When you try to calculate those, what number goes in the denominator of all those? 1,012, the total. What number goes in the numerators? Whatever row you're looking at is the number that goes in the numerator. So if you're looking at women and no college, you're going to have 195 divided by 1,012. That's what they did there, right? So I want to look at this one just a second here. 63.7% said outside the home, 32.8% said stay at home, take care of the home and family, and 3.5% said no preference. Do you understand that in this table, the majority of the individuals want to get a job outside the home? I'm just looking at the numbers, right? Can I make a bar graph of this for you? Sure. You want to look at preferred lifestyle? Give me 3 of them, right? Job outside the home, job to stay in the house, take care of the family, home and family, no preference, heights of bars. Yeah? That's a chapter 1 thing. Now, what about if we look at these percentages here that are on the bottom of page 164, the one about calculating the marginal distribution of sex and education? Do you notice anything about those percentages? Look, go to figure 6.1. They made a bar graph of it for you. Do you notice that you're looking, it's irregardless of what the person said about preferred lifestyle, now you're looking at sex and education. You notice what group there had the highest percentage? Men with college, right? What group had the next highest percentage? I'm reading the heights of the bars in figure 6.1. Hell, I can read the percentages here on the bottom of the page. 38.3% of the people in this table were men with college. 29.9% were women with college. And then we went down to 19.3%, women no college, men no college, 12.5%. So, I'm still seeing what I see here, right? Here, oh yeah, the majority preferred to have a job outside the home. In this table, it looks like the highest percentage of people in this table had some kind of college, right? Whether it was male or females. Okay? The reason I'm talking so much about this one is because there's one other type of distribution here. Marginal distribution can't be a problem. Right? You're using the totals, row totals or column totals to calculate it, right? The other type is where we're going to start on Tuesday. And there's something called conditional distributions. Now, that ain't as clean as just using row totals or column totals over a table total. Somewhere along the line, we've got to use the numbers in the body of the table, right? The numbers that actually were given to us. Now, if I have an R by C table, and then I'm going to shut up and we're going to give you a test back, we're going to have that little chop. Right? Number of rows by the number of columns. I always told you there's 2 marginal distributions, no matter how many rows or how many columns. There are always R plus C conditional distributions. Now look, we're in chapter 6. We're in the chunk of the book 4 through 6 where we're supposed to be looking at relationships between 2 variables. Here, chapter 6, we're looking at relationships between 2 categorical variables. Marginal distributions tell you nothing about the relationship between the 2 variables, categorical variables in your 2-way table. What tells you about the relationship? The conditional distributions are where we're going to start looking at the relationship between the 2 variables, because all this crap back here I did, they don't tell you nothing about the relationship. Hell, you ignored the other variable. Example 6.2 don't tell you anything about the relationship. You ignored the lifestyle, right? So what we have to do is we have to deal with these conditional distributions. Now look, this comes down to calculating percentages. What did I do since I started here? It's calculating percentages. Now, we'll pick up there on Tuesday. When you get your test back, right, you're going to see a number out of 40. There was 40 questions, so I wrote on there how many you got right out of 40. If you want to feel like you want a letter grade here, take the number, divide by 40. If you're in the 90s, that's an A. In the 80s, that's a B. 70s is a C. 60s is a D. Less than 60s, an F. If you want to know how many points you're going to get out of 200 on that test, take the number you got right and multiply by 5, right? They were all worth 5. For your midterm grade, here's how I'm going to calculate. You've got, how many homeworks we got up till now? 4? The first one was like out of 16. Does that sound right? Hell, I can't remember what it was out of. I'm going to make that up. I think it was 16. The second one was out of 19. The third one was out of 12. And the last one was out of 6. I'm going to take these and add these together. And I'm going to get a number here. I'm going to take these. And I'm going to put that number there. I'm going to divide. If you're in the 90s, you're going to get an A. If you're in the 80s, you're going to get a B. So on and so forth. I don't do any pluses and minuses at midterm. I don't think anything about attendance at midterm. I don't think anything about the launch, the pad, the learning curve things at midterm. I don't think anything about the class survey you did is going to get 5 points. It's based off that first test and those 4 homeworks, and that's how I'm going to do it. All right? So, Rob, go ahead and give it back to him. Wrong one. Wasn't even close. Right one.